my talk today will look at the importance of the pre-industrial baseline in determining the likelihood of exceeding the Paris limits. And this really begins from where Neroli Abraham's talk ended on the first morning of this meeting. So his work I've been doing in collaboration with Mike Mann, Ed Hawkins, Gabby Hagel, and Simon Tett. And this is the motivation of all of this really is the Paris Agreement, which was signed in 2015. And in this agreement, nations of the world agreed to holding the increase in the global average temperature to well below 2 degrees above pre-industrial levels and pursuing efforts to limit the temperature increase to 1.5 degrees. So here the really important part is this pre-industrial levels. This was not really defined. And indeed, although this talk won't really concentrate on this too much, what temperature means wasn't really defined either. So we're going to be looking at the importance of the definition of this pre-industrial to the likelihood of exceedances. And our starting point of this talk are the global, CMIP 5 models. We're using the historical runs with the future projections added on. So we're looking at RCP 2.6, RCP 4.5, and RCP 8.5. So here's different scenarios where 2.6 has got a lot of mitigation going towards 8.5, which is the business as usual scenario. So the setup we're using, we're looking at global annual mean temperatures. Everything I show will be global annual mean temperatures. But unlike a lot of studies, we're actually looking at a blend of SATs and surface air temperatures and surface and SSTs. And the reason why we're doing this is because we think that how are we going to say whether we have passed 1.5 or 2 degrees is by using blended temperature data sets such as Hagru T4, which is a blend of SATs and SSTs. So when we're using models, it's important to actually use the same thing. And our setup is quite simple. So we're interested in the temperature since pre-industrial. But first, we're going to calculate temperature with anomaly from 1986 to 2005. And then we're going to add on the warming that we think has happened since pre-industrial. And this is because we trust the observations more than we trust the models. And we're going to break down the warming since pre-industrial into these two components. So this could be pre-industrial, I suppose. This is the industrial warming. So this is the warming after 1850. This is going to come from observations. And this is the factor we're really interested here. This is warming before 1850, and we're going to determine how important that is for our likelihood estimations. I should say all exceedances are going to be based on 5-year mean temperatures, and this is to avoid any early exceedances due to ENSO events and the like. So the first question we should ask is if we're going to use, sorry, I should say the results on the top here, these are all shown assuming that the warming before 1850 is negligible. So this is what was shown in the IPCC report. In that report, they made no mention of pre-industrial. They just defined everything from an 1850 to 1900 baseline. So how reasonable is it to use an 1850 to 1900 baseline? How unusual is this period? So if you look at volcanic activity, and this is using the Crowley and Unterman data set. So here we're plotting the mean of 50-year chunks of volcanic AOD in the 4 latitudinal bands defined by this is just coming straight from their data set. So we've highlighted 1850 to 1900 in blue, and this is all the historic volcanic aerosol. And as you can see here, perhaps 1850 to 1900 is not that unusual compared to the long-term mean of volcanic activity. The same is also true for solar. So again, these are two different total stellar irradiance data sets, Vieira et al. And Steinhilber et al. And these were used for the last PMIP 3 simulations. And as you can see here, the 1850 to 1900 is highlighted in blue. And again, perhaps this period isn't actually that unusual for natural forcings. So we're going to turn to the models. We've used 7 models. Some of these have got several ensemble members. In everything we've done, we've weighted down models with more ensemble members so that each model can contribute equally. And here is the mean. temperature anomaly relative to 1850 to 1900, and this is calculated as his global mean temperature with a blend of SATs and SSTs. And on the top, you can see the 100-year, the centennial means. And I think what's clear here is it really does depend on the period you're looking at. So this is all differences between up to 1850 to 1900. So you have some periods, for example, when the Tambora has happened and when there's Dalton minimum, you have quite low temperatures, whereas some periods are actually quite, there's periods in the past that are actually quite similar to the 1850 to 1900. So this makes defining a pre-industrial baseline very tricky. Another way you can do is you can ask what is the anthropogenic cause of this. So you can look at, so here we're looking at the greenhouse gas only runs. Here we've only got 3 models. We're looking at CSM, CSIRO, and HADCM3. And this is the 3 models plotted here. I think what's clear here is that relative to 1850 to 1900, all times the greenhouse gas is cooler than that period. And this is due to the early industrial period, starting from the 18th century. So if you look at the 100-year means, here again there's a bit of variance, but less variance, and they're generally between like 0.1 degrees cooler to about 0.2 degrees. And then turning to the natural forcings, we have volcanic and solar. In these models, the solar forcing is quite weak, so there is little change due to solar forcing. But the volcanic forcing, on the other hand, is really showing quite a large centennial behaviour. And that's causing the differences in a lot of the differences coming from this all-forced run. So there are periods with like Tambora, it's quite cool. And the absence of volcanoes also makes those periods such as the 16th century, relatively warm. So if we're interested in how large was warming before 1850, well, what we're going to do is we're going to look at all the 100-year periods between 1400 to 1800, and we're just going to form a distribution of all of this. So in the top, this is all forcings. As you can see here, the answer to this question, how large was warming before 1850, it depends. It depends on the pre-industrial period you pick. It depends on the model you're looking at. The answer lies somewhere between 0 and 0.2. So here's a 5 to 95% range on the top. If we look at the different individual forcings, greenhouse gases, yes, the answer is again somewhere between 0 and 0.2. So I think the answer is, if you're interested in this pre-industrial baseline, the answer probably lies somewhere between 0 and 0.2, and that's what we've looked at going forward. So what we've done is we've added these temperatures, like 0, we looked at no difference. We looked at no warming for 1850s, 1900s, a warming of 0.1 degrees before that period, and a warming of 0.2 degrees before that period. We've added that onto the model runs to work out what difference that will make to the likelihood of threshold exceedances. So on the top panel here, you have the distribution of models. This is now using CMIP5 historical and the future scenarios, and this is the warming in the end of this century. So this is now the temperature from pre-industrial. So if you assume that that pre-industrial is actually the same as 1850 to 1900, this is what you get. So you get a 61% chance of exceeding, this is 1.5 degrees under RCP 2.6. If, on the other hand, you assume there's already been 0.2 degrees of warming up until that point, this increases to 88%. So although we're talking about quite a small difference, only 0.2 degrees, it can have quite a large effect on these all-important threshold exceedances. And the same is also true a little bit for RCP 8.4.5. So you can look at, there is 0 chance of keeping it below 1.5 degrees in this scenario, but there is a chance of keeping below 2 degrees. But this chance decreases depending on how much warming we've already had since this 1850 to 1900 baseline. And equally, if we're interested in the year of temperature threshold exceedance, so here's, I'm plotting here when 50% of model runs are above the threshold. As you can see, this is very dependent on the amount of warming that's happened up until 1850 to 1900. So if you concentrate on the RCP 2.6, which is here, you can see if there's 0 warming, so this is, the blue is the likelihood of exceedance of 1.5 degrees. we're likely to cross this in 2040. There'll be no warming since before 1850, but it's going to be much, much sooner if there has been up to 0.2 degrees warming. Okay. And this is just another way of plotting this information. So this is the likelihood of threshold exceedances shown by the colour of the shading. This is now the assumed warming before 1986, 2005. So the observations put us at about 0.65. That's from 1850 to 1900. But then if we assume, so this is then if you assume 0.1 degrees warming before that period and 0.2 degrees warming for that period. And as you can see, certainly for the RCP 2.6, it matters quite a lot whether we lie on the dotted line or the solid line. Although for RCP 8.5, it really doesn't matter a lot. It doesn't matter at all by the end of the decade. We're going to pass it regardless. So how important what I'm talking about is really depends on the scenario and the yeah. So finally, I'm just going to whip through this. This is what, as well as having an effect on the likelihood of exceedances, it also has an effect on carbon budgets. So in the this is a figure from the IPCC. Here we're plotting. Here's how carbon budgets are typically done. We've got temperature relative to 1861 to 1880 on the y-axis, plotted against cumulative carbon emissions from 1870. So this is fine. This is very self-consistent. But if we suddenly want to work this out, how much carbon we can burn to keep temperatures below a threshold relative to true pre-industrial, this axis has to change, and this effect has. I'm not sure I've really got time to go through all this, but the effect is if we have a warming of 0.1 degrees up until before this period of time, this accounts for 20% of the budget still remaining in 2011. So we're talking about quite a sizable amount. And if the warming is 0.2 degrees, it means we have 40% less of our remaining budget left. So clearly that's, we're talking about something very important here. So I've been told that my time is running out, so I'll leave you with my conclusions. And yeah, thank you for listening.
So I agree that this is a really interesting scientific question. I wonder if you have any thoughts on how we communicate this to people who are actually making decisions based on Paris.
Yes, so I didn't really get to my conclusions, but it's here. I think what is key here is that, I mean, we're not really talking about anything particularly real here. We're just talking about language in many ways. It's all due to how the Paris definition was defined. I don't think we should get too hung up on trying to work out these values as such. I think the paper is really to highlight that it can be potentially quite confusing, and that there is, it can be quite important. I mean, my recommendation would be very similar to what I think I've taken this from Ed Hawkins' paper that came out last year. And I think that really, what would be really important is to reach a consensus about what we actually mean by pre-industrial, not to try and fight over what actually pre-industrial was, if that kind of makes sense. So I think we just need to define this better to have So I think it's very important not to communicate, to try and communicate to the public that rather than, different 0.1, 0.2, that kind of thing.
Yes, today I'm going to show some results from an ongoing effort actually to reconstruct global mean temperatures over the Common Era based on the new Pages2K proxy database. Now, first, it's important to say that this is a so-called Pages2K transregional project, which means that we have a range of persons from all over the globe that have contributed to the results that I'm going to show today. So what's the context of our project? I like to illustrate this with this figure here from the last IPCC report that actually synthesizes the Northern Hemisphere mean temperature reconstructions that were available at that time. So each of these lines represents temperature reconstructions over the Northern Hemisphere. Now we can see some nice agreements between the methods, like little ice edge cooling and maybe a warm peak around the year 1000, but there's also some very obvious discrepancies among the different reconstructions. Now, the issue here is that all these reconstructions are based on different input data sets, different target data sets, different target seasons, even target domains, and obviously different reconstruction methods. So it's actually very difficult to interpret the differences between these lines, if not impossible. And if you look at the global scale, we see that we have much less reconstructions, and they hardly extend over the full 2000 years. So the aim of the project I'm presenting today is to actually do a range of global mean temperature reconstruction based on consistent input data, so that we have in the end a set of reconstructions that are better comparable and to use for data model comparisons and another analysis. And we think this is timely because the new Pages2K proxy temperature database has just been accepted and will now be publicly available. And you see here the data sets that we have available. So we have 692 records from all over the globe, and you see that's quite an advance since the 2013 version of Pages2K, where we had only 501 records available. But still it's important to note that there's quite a clear spatial bias here towards the northern hemisphere, where we have many more records. And also if you look at the evolution of the data available in time.
The sound's not good for on the back. We will try the other microphone for you.
Okay.
Okay, just
yeah.
We will give you 5 more seconds.
Oh, that's very kind. Is it better now? Can anyone hear me? Is it not too loud? Okay. So that's the temporal evolution of the proxy data in this new database, and you see that most of the records extend maybe 400, 450 years, and then the amount of data decreases considerably, and at the beginning of the Common Era we have less than a third of all the records available. But that's what we have, and that's what we use. And apart from that, as a reconstruction target for all our reconstruction, we use the Coulton and Way global mean surface temperature data set over an April to March seasonal window. All our reconstructions are calibrated over 1916 to 1995, and we keep 1881 to 1915 for independent validation, reconstructing the full Common Era. And important to note, all our reconstructions are based on ensembles that also allow interpretation of the results based on the ensembles. So what records do we actually, or what methods do we actually use for our reconstructions? You see the 8 methods here, a bit subjectively sorted by increasing complexity. The top ones are widely used methods from the past with relatively simple statistical techniques, composite plus scale, principal component regression. We also use the Manettal implementation of RegEM, and then some more recent and more advanced methods like pairwise comparison, optimized information extraction, Bayesian hierarchical model as implemented by Barbosa et al., and 2 versions of offline data assimilation that also take information from climate models into account. The last one here is in brackets because the reconstruction doesn't cover the full 2,000 years, so I'm not going to show it to avoid confusions, but we use it for important sensitivity tests. So how do the results look like with all of these methods? Let's have first a look at the instrumental period. Black is our instrumental target, and the different colors are the different reconstruction methods. So non-surprisingly, we have a very good agreement over the calibration period, and prior to that, it still looks quite good, but you can see that there is increasing also a little bit of discrepancy. So let's have a closer look at the validation periods to see how the different reconstructions compare. So these are validation statistics for all of the methods. You see here 4 different validation statistics. I'm not going into detail here. The important thing is that they're displayed in a way that high values towards the top of the slide means high skill, and lower values means low skill for all of these methods. The median across all reconstructions is shown with the dotted lines. Box plots are validation skills across the ensembles, and the circles are for the ensemble median. Now I'd like to stress here is that really you can see that there's very similar performance of all the different reconstruction methods. If you look at the RMSE, for example, they're hardly distinguishable. So based on the validation statistics alone, we cannot identify an objectively best or worst reconstruction method. And it's also interesting that even the very simple methods like composite plus scale perform similar in all the other methods. Now an important question is, how does this look over time? So this is now the root mean square error for the different methods in its original scale, so higher values means higher errors. And this is based on a fixed proxy network experiment where we just do several reconstructions based on the proxies that are available back in time. So this means that these lines here represent the root mean square errors of the reconstructions only using the proxies that extend over the full 2,000 years. and here the proxies that extend until the year 500. And you can see here a very big difference, which means that actually prior to the year 500, the proxies that we do have yield much larger errors in our reconstructions, and after that, the decrease in the error is still visible, but much smaller. So we really have to note that the uncertainties are high at the very beginning. So finally, let's have a look at the actual reconstructions. You can see that these are 30-year filtered reconstructions. Black line is the instrumental target again, and this is importantly relative to our 1916 to 1995 reference period. So what we see first is that the cooling trend over the pre-industrial common era that has been mentioned many times yesterday is clearly visible also in our results, but we still have some troubles with capturing the actual low-frequency amplitude. So you can see that the amount of little ice age cooling and also the amount of the trend over the pre-industrial common era is quite different across the different methods. So we still have a lot of work to do to tackle this, actually. But the good news is, if you look at the decadal to multi-decadal timescales, there's an extremely good agreement across the methods. If you look at the different wiggles here, some of them are caused by the volcanic eruption, but actually across the full time period, all the reconstructions are extremely highly correlated at the multi-decadal timescales. Now, these are all the ensemble medians, and the question is, how does it look like if you also try to incorporate the reconstruction uncertainties? Do we still have agreement across the methods? I try to illustrate this with this figure here. So to display this, we just added up the density functions for each ensemble for each year, so that they sum up to a value of 1 for each year. So darker values here means higher probability for a given temperature at a given year. And you see that we have relatively sharp the dark values over the last, let's say, 800 years, and then the further we go back in time, it gets more smeared and blurred. So we have more uncertainties. So we have maybe the best agreement here in the 1450s cooling period, and you see that at the very beginning of the reconstruction period, we cannot confidently say whether temperatures were higher or below our 20th century calibration period. Now, how does this compare to earlier reconstructions or climate models? To illustrate this, I'd like to first go back to another IPCC figure that you probably all have seen before. This is now, again, the gray shading showing that the reconstructions that were available at the time of the IPCC report, and the colored lines are the thick line is the mean from a range of model simulations, and the thin lines are the 90% range from the model simulation. And you see at that time there was still a discrepancy, particularly here in the medieval times, where we had warmer reconstructions and colder models until about 1400. Now this is with the reference period of 1500 to 1850. How does this look like with our updated reconstructions? You can see here the adapted figure. It's not one-to-one comparable because we use different model simulations here, but importantly, what I like to show is that we don't have this disagreement anymore in the medieval period, so the warm peak in the reconstructions actually disappeared. We even see some cooling here in the early 12th century, potentially related to the 1109 eruption. And you can also see that we have still a bit less cooling in the reconstructions for the Somalis eruption, but the nice agreement here again in the 1450s. So I think the new reconstructions really improve also the agreement with the model data. Yeah. Last but not least, the context of 20th century warms. That's always a question we get many times. So to display this, I have for each ensemble member of each method just calculated the 30-year running averages. And then this figure here displays over what period the warmest 30-year period actually occurs. And you can see that in almost exactly 2/3 of all ensembles across the method, this happens over the last 50 years. Just for two methods, that's the warmest periods are at the very beginning of the reconstruction period, and these are actually obviously the reconstruction method that gives us the strongest pre-industrial trends, so they have the strongest warming here at the beginning, where our reconstructions are also much more uncertain. So to conclude, we have a new set of global mean surface temperature reconstructions with consistent input data that can now be used for further analysis. We have generally very similar skill across the different methods, but large uncertainties at the very beginning of the reconstruction period. We have a good intermediate agreement on the decadal to multi-decadal timescales, but still problems at the lower frequencies. And the late 20th century temperatures appear exceptional in 2/3 of our ensemble members. Thank you for your attention.
You have a lot of trimming data in there. It looks like you're calibrating to annual temperatures. Is that going to be an issue?
It's probably going to be a little bit of an issue, but I mean, it's difficult to come up with a season that we could use for the global mean, because obviously in the south the growing season is different than in the north. But that's actually what we're tackling with some sensitivity tests with the different methods. So the one data simulation method that we have shows actually that for some region it actually does make a difference, but for the global mean, if I remember correctly, the differences are rather small.
And how about processing of the trimming data with regards to the trending? I mean, do you do an ensemble approach per site for that as well?
No. So in this case, we really use directed input from the page2k database. So, and in the database, there's no consistent detrending or so. So they're based on the method that have been used by the individual research that have contributed to data. Yes.
I will ask a second question. Have you tried to understand why the different methods reproduce differently the low frequency? So we know that it's always a problem, but why the method behaves differently?
Yeah, that's what we have to look at a bit now. So one thing I have to mention here is that most of the methods are still only able to incorporate like the high frequency proxies. And some of them can also do the low frequency proxies, and these tend to be, in the figure, the ones that show the strongest pre-industrial cooling trend. So that's one thing that's probably responsible for the differences.
I'm going to step into the spatial domain now after having seen these global mean reconstructions. It's interesting to look at what things look over space. And I want to acknowledge the last Millennium Reanalysis team, primarily my postdoc, Michael Erb, who's done a lot of the heavy lifting for the reconstructions that you're about to see, as well as the rest of the team. I, of course, want to acknowledge the wonderful work by the whole Pages2K consortium, many of whom are sitting in this room right now, and also a few of the people who have collaborated with me over the years or more recently. So, I want to tackle a couple of science questions with this. One of them is related to this question of how unusual is the current warming. I'll then step into the LMR methodology to describe it a little bit more. I will tackle the volcanic response, the solar response, and there will be a lot of open questions at the end. All right, so as Raphael pointed out, it's not very instructive to just look at the median. So we actually, the beauty of the data assimilation method, or at least an ensemble-based method, is that you have a full range of uncertainty that travels along with the methodology. So you have the median in black, you have the 95% highest density region in dark blue over here, and a number of ensemble members there. And very simply, okay, we learned a lot from that, and we can ask about how reliable this whole thing is, but one of the favorite exercises in our community is to take these two periods and ask what is the difference between them. So I'm not going to do that, because as Diaz et al. Pointed out, it's probably not the best way of thinking about Earth climate. But we are going to look at space. So what does the last Millennium Reanalysis consist of? It's fundamentally a way to integrate information from climate models over here, from proxy data, of course, and in this case we've restricted ourselves to annual proxy data. So we have trees, corals, and ice cores, but we actually also have varved lake sediments. And there's an ensemble Kalman filter that updates the model states according to how consistent they are with the proxy data, and the glue that binds them together are proxy system models that can bridge from the model states to the observation space. In other words, they take temperature and delta 18 and they can make a coral out of it, or a tree, or something like that. Now, that's the ideal way in which this methodology functions. In practice, we found, when we started this work, we thought we would have a lot of millennial length model outputs that incorporated water isotopes so that we would be able to do this forward modeling. And so far, we haven't gotten our hands on a lot of these reconstructions. So what I'm going to show you today is pretty disappointing from the proxy system modeling point of view, because we've had to simply take a calibration, like a very standard calibration. The only advantage is that we are expressing proxies as a function of climate and not climate as a function of proxies, as is often done. But there's a lot of room for growth in that. In the future, we really hope to be able to leverage isotope-enabled simulations, and that's a call to all of the modelers out there that it should be part of the standard PMIP package, that every single simulation should have water isotopes in it, because that's the only way to truly compare to most of the observations. I know, easier said than done. So fundamentally, what do we get from all these components? From the climate models, we chiefly get the spatial relationships. And even more importantly, we get the relationships between different fields. So one of the beauties of this method is that we can reconstruct not just temperature, but also other fields like moisture availability, sea level pressure, and other things. So that's one of the great promises of data assimilation, and you'll hear more about this in other talks in this session. The timing is what we get from the proxies. So all of the wiggles that you see in time come entirely from the proxies. If the proxies are not informing these reconstructions, they would be completely flat. So the models give us space, the proxies give us time, and the amplitude is controlled by these proxy system models. So we take this, and in the case of the reconstructions I'm going to show you today, we took all the annually resolved records from the latest Pages 2K Phase 2 compilation. So it's definitely a subset of the full one. And as Rafi pointed out, that might be important to keep in mind when you look at the contrast between what other methods are giving, if those methods are using the full range of records, including, for example, marine sediments. And then we use a HADCRU 4.4 to calibrate our proxies against. And then we get a solution. So here's how this solution behaves over the instrumental period. So the black line is the median, the 90% high density region is in gray, and you can see it compare here to a number of calibration data sets. And you don't need a degree in statistics to see that this is an awfully good fit. The calibration in space, I don't have the figure here, but it looks actually quite reasonable in most places. The places where it doesn't is where the models already had trouble representing things. So there's a cold tongue bias in the model that we use, and we see that expressed in the verification statistics. So it's one of the downsides of using models as part of this, is that you inherit the spatial biases of the models. But you do get the perk that you're able to reconstruct many fields at once. However, today I'll mostly focus on temperature. So here's what those ensembles look like, right? And here's perhaps a clearer version, which has been low-pass filtered. And one of the questions we want to ask is, do we live in extraordinary times? So if you draw a line here and you compare the temperature of the past decade or so, or the past 25 or 50 or even 100 years, how do they compare to equivalent periods in the Common Era? And here is one analysis of that. Once again, the beauty of ensembles is that you can start doing some meaningful statistics. So here are 4 examples using either the last 10 years, the last 25 years, the last 50 years, or the last 100 years. And you can ask for every single case, so you get a range of ensembles, and you can say, what is the distribution of these, in this case, global mean temperature on these intervals, and how does it compare to the past? And you can see that in most cases, you can very clearly distinguish the present time or the most recent time, that it's very clearly distinct from what happened before. Only when you start to approach the century timescale do you get a result where the 20th century doesn't look that much warmer than everything else. But if you look at shorter intervals, including decades, you get a very clear separation. And to me, this is a relatively this is an expected result. What is perhaps more interesting is to look at the rate of change over time. And here, if you look at decadal warming rates, for example, you find that the current, or the last 10 years of warming, is not that exceptional. I mean, it's markedly higher than most, but not all of them. And I think most of what you see here in the gray area actually corresponds to recovery from volcanic coolings. So, you know, those happen to be about as abrupt as the current warming. But when you start lengthening those periods to 25, 50 years, or even 100 years, then you get very sharply defined rates. And there's only very few ensemble members that seem distinct from that. So, you know, perhaps it's on 50 or 25 years that we find the most clearly defined difference between the current time and the common era. Okay, I promised you some space, so let's get on with it. I tried very hard to do the same analysis over space, but I didn't actually manage to get it done in time for this, this workshop. However, a simple way of looking at this is to ask, you take the warming rate on 100-year periods and you ask, in what fraction of the ensemble members is the latest period, that is to say the 20th century, warmer than anything before? Or not warmer, but is the rate higher than anything before? And you can see that overwhelmingly over almost all of the reconstructed domain, and the .cr where we have proxy data, you can see that it's that the 20th century is rising as an anomalously high rate, and it's only in these areas around Antarctica where we don't happen to have a ton of data that we don't find this results. So I would argue that we are living in extraordinary times. Okay, as I said, a lot of people like to focus on the Little Ice Age or the medieval climate anomaly, so let's do it for good time's sake. You see a very strong polar amplification of this cooling, you know, very strongly expressed over the Arctic as well as Western North America. But there's, in general, cooling all over the globe, not terribly surprising. What is a little more surprising is when you look at the medieval climate anomaly, it actually, there's almost nowhere except Eastern North America where you actually see any warming compared to the calibration period, which is here. So this is a little bit suspicious to me because, if anything, you know, there's legitimate debate about just how warm the medieval warm period was, and that's why we don't call it that anymore. But we do know that Iceland was quite a bit warmer. If, you know, otherwise Eric the Red would never have been able to cross over and to conquer, to create, establish colonies in Greenland. So I think there are quite a few caveats here, and I want to look more into why we obtained this result. Okay, if you look at the difference between the medieval climate anomaly and the Little Ice Age, not the shock of titans, perhaps the shock of midgets, you get a pattern like this, which, as you see, is looking fairly different from Mann et al. 2009, which has become the canon by which every single climate model is evaluated. I would like to point out, as we've shown fairly recently, that if you use a number of other methodologies, including the one used by Mann et al. 2009, but using the previous Pages 2K database, in fact, a range of methods and a range of databases, you never find the same pattern. So that pattern is not robust. And in fact, the pattern that you do tend to see is fairly consistent with what most PMIP3 models have shown. Okay, I have 2 minutes to describe the relationship. I have 2 seconds. Okay, interesting. Well, if you want to know more, you'll just have to find out with me. So, okay, let's go to, let's fast forward to the conclusions then. Well, I'm just going to leave this here and take questions, and maybe that'll give me the opportunity to show other slides.
Well, why do you call it reanalysis? For me, it's just a new reconstruction method. And I'm a bit maybe a mean person here in the whole conference, always talking about naming. But I think it's really, the expectation of a reanalysis is different compared what you have presented at the moment. So for me, it's a new reconstruction, and it's fine, but a reanalysis should incorporate more than just, say, annual mean things. It's just incorporating model knowledge with proxy knowledge, and I think this is not enough for calling it reconstruction, reanalysis.
So can you clarify what are your expectations? What constitutes a reanalysis then?
Well, it's an analysis.
It's using the observations, in this case proxy observations, within a model using some statistical methods on, I would say, having also daily to sub-daily scale data.
Okay. All right. Well, if you can reconstruct the climate of the past millennium at daily scale, I definitely want to have a conversation.
All right. So I'm another data simulation guy, so if you want to get mad at me too, go ahead. In fact, my work is kind of the basis of the LMR project, so we can chat too. Okay, so I'm going to be talking about, this is complementary work with what Raphi showed earlier. What we're basically interested in is throwing a bunch of different methods at reconstructing the past 2,000 years, but do it spatially, not just global mean, like what Raphi said, or showed before. So the basic question that motivates us, or motivates this work, is why are reconstructions different? And Raphi talked a little bit about this earlier. Certainly it's because of probably the data as well as the methods, maybe both. And so it's hard to isolate what exactly is different when you get the spaghetti plots that we show, say, in the IPCC. Our interest in this is also motivated by questions related that were recently brought up by Jing and Julien, where they did reconstructions. Julien mentioned this just barely, where you do different reconstructions using the same proxy data, and you can get very different answers when you do something like take the medieval climate anomaly, subtract it from the Little Ice Age. And these differences are completely due to the methodological differences. They use the same underlying proxy data. And so we were interested in what do your spatial reconstructions look like, how they look differently when you use different methods, but maybe more importantly, what's robust across methods. So what can we say that's really robust? So the proxy database that we're going to be using is the recent Pages 2K proxy database. As you can tell, it has a wide variety of proxies, a huge chunk of trees, especially in the past 500 years. And we're interested here in this global reconstruction. And we're going to throw at this reconstruction 6 different methodologies. Be familiar probably with some of these in the top, and just speaking very broad brush, I obviously don't have time to go into a lot of detail about the differences in the methodologies, but we can say the top 4 are essentially traditional regression-based methodologies that have been updated and improved since the early days of climate field reconstructions. And then the bottom 2 methods are basically climate model-based reconstruction methods. So one is an analog method, basically chooses the best climate model state. And then data assimilation, which is an actual fusion, statistical fusion of the proxies and the climate models. So for this reconstruction framework, it's very similar to what Raphi showed earlier. We have HAGCRU as a target data set that's particularly important for the regression-based methodologies. It's less tied to the reconstructions for the analog and the data assimilation method. They deal with HAGCRU a little bit differently, a little more sophisticated fashion. And then we're doing an annual average where we define the annual mean as April to the following calendar year March, which we've had to do because calendar years really don't make sense climatologically, nor does it make sense when you're using proxies across both the northern and the southern hemisphere. And then the reconstruction is over the full Common Era. And just to show, the calibration interval was the early to late 1900s, and validation late 1800s to early 1900s. And this is just the global mean temperature, just to give you a feel for how the different reconstruction methodologies did over that time. I'll be showing some spatial skill next. So what I'm showing here is 4 different metrics where we've summarized basically spatial skill maps, and we've condensed them into box plots. And we have, for each different method, we have 4 different skill metrics. The continuous ranked probability score, which is an ensemble-based skill metric, so it doesn't just test the mean, but it tests how well is your full probabilistic reconstruction doing. We have the traditional RE, root mean squared error, and correlation. And as you move from the left to the right, you go from low skill to high skill, so the further over to the right you are, the better your reconstructions are doing. And just like what Rafi said before, we don't see that there's some objectively best method for reconstructing temperature. There are differences, but by and large, you wouldn't be able to stand here and say, okay, well, you know, principal component regression is the best one. They're really doing roughly similar in terms of the skill metrics. The spatial patterns are also quite similar. I'm not going to show those, but they're quite similar across the methodologies. Okay, so there are a lot of cool questions that one could address with all these reconstructions. The questions that I'll be focusing on are a few related to trends over the past 2,000 years, especially the pre-industrial era. What's robust across all these different methods over the pre-industrial era or over the past 2,000 years? So if we look first at the cooling trend, so we take the ensemble mean of all the different reconstruction methods, and then we compute the trend from the year 1 to 1850. And we see that over that trend, over that era, over most of the globe, we have cooling, though there are quite a few places on Earth where the trend is flat or even warming over that time period for this ensemble mean of all the reconstructions. And the proxy locations are indicated with those green circles. Another way of looking at this is asking what's the fraction of global area that's warm or cold with respect to the whole reconstruction anomaly. So we just take the mean of the entire reconstruction and then ask how many locations or the fraction of locations over the globe that are warm or cold during that era. And so basically we see, if we look towards the present, we see the clear global warming signal where most of the Earth is very warm. Roughly the little Ice Age era, a lot of the locations are cold. And then as we go further back in time, a lot of locations begin to warm again. But notice, just like in the previous figure, it's not obviously a completely global cooling or a completely global warming. There are some places where you have warming, some places where you have cooling in any given 30-year chunk or 10-year chunk. All right, so then another kind of question is, how well do the reconstructions compare against a model simulation? And just since it was easy for me to get was the CESM Last Millennium Ensemble, and I'm showing here the global mean temperature reconstruction as well as the CESM ensemble mean of all of their fully forced simulations. And so the first thing that really struck out to me was that they compare so well, especially like at centennial timescales to decadal timescales. If you take the trend, they're essentially identical trends over this era, which sort of shocked me that it did so well for the global mean. And then if you look, how well does that do spatially? And I show this information using distributions here. They're really very comparable distributions. Maybe in the reconstructions we have more areas where the trend is positive, whereas the climate model maybe has a little bit more areas where it's cooler, but by and large, very comparable between the reconstructions and CESM Last Millennium Ensemble. I will note that 2 of the reconstruction methods, if you recall, use climate models. If you pull those 2 methods out, the analog method and the DA method, this result still holds. So using the Pages 2K data and our different methodologies, we get surprisingly good agreement between the CESM Last Millennium simulations and our reconstructions. All right, so considering all the uncertainties, our recent years the warmest of the past 2,000. So if you take account of all the ensembles from all the reconstructions, and we simply ask, what's the probability that the warmest year happened within the past kind of 20 years, roughly, from the 1980 to 2000? For a lot of locations, we do get that we have a high probability of it being the warmest year happening during that 20-year period. But there are also a lot of locations where, given the uncertainties, we can't say that the warmest era happened. And maybe in certain locations, almost certainly, it didn't happen, where the probabilities are very low that the warmest year came during the period from 1980 to 2000. All right, and then to conclusions. We have a new set of global temperature reconstructions based on consistent input data. They show similar skill characteristics. There are differences, but on kind of a broad scale, they're very similar. Pre-industrial cooling trend happens in most locations, but not all. These reconstructions compare very well with the CESM last millennium ensemble. And recent warmth, slightly unprecedented over many locations, but definitely not all, given the uncertainties. Thank you.
Thank you for that. In that last plot you showed looking at the probability of the hottest year occurring,
yeah.
Why does that terminate in 2000?
Because we ended the reconstructions in the year 2000. A lot of the proxy data falls off. Like even in the 1990s, it's like a really steep decline in the number of proxies, so we stopped our reconstruction then.
So do you think that would change if you extended that to 2016?
Potentially. There are a lot of locations where the early, year 100, say, CE, it's quite warm. Again, given the uncertainties. So the uncertainties are quite large too. So considering both, then no, we can't say that it's the warmest. Yeah.
There is two other questions here.
Yeah, but I've got the mic.
Okay, all right, Jason, go for it.
So the probabilities here are based on the spread over the ensemble, but that doesn't include the reconstruction uncertainties, the spatial skill uncertainties associated with each of your reconstructions.
It does.
So you've included those into these assessments?
Yeah, so that's why, that might be a big reason of why there aren't more places that are warmer, is because there's just a lot of uncertainty early in the reconstructions, and so the error bars are just really big, yeah.
Can you comment on this pattern as to whether or not it mimics or it looks like the uncertainty or the skill assessments across all of, how different are the skill assessments across all of the reconstruction methods in terms of their spatial skill?
So yeah, there is similarity in this pattern to where they, where the reconstructions do well. Yeah, there is some similarity, but it's not like, it's a carbon copy of that map where it's just in the places where we're doing well, where we're confident about the trend. So there is some overlap, but not completely.
Since you divided the reconstructions between the regression-based ones and the data assimilation,
are you going to quibble?
No.
Oh, okay.
I like that. I'm asking, a similar question is that if you do the same map, but for every single reconstruction, or for the regression-based methods and the DA-based methods, do they look different? I haven't done that yet, so it would be good to look at. Yeah.
It's actually a question of both of you people who are doing the data assimilation-like methods. So as the data drop off over time, you'd expect for a system of data assimilation, there's less information, and so the resolved, reconstructed, or estimated amplitude of the variation should shrink, and you should tend toward climatology with error of the variance of the signal. That doesn't seem to be the case. But correct me if I'm wrong, and if...
It is the case.
It is the case?
Yeah.
Okay. So how do you deal with that bias in the amplitude of reconstructed variation over time and space in your further analyses here?
I guess I don't quite understand the question. Like, how do I deal with it? What do you mean? Yeah.
For instance, if you were looking at a change in variance over time, you would see an increase in variance over time because there's more observations.
Okay, yeah. So, I'm not asking. So that's part of the questions that we're asking. We're trying to stay away from, You know, I'm not asking the question, was ENSO variant, for example, I'm not asking the question, was ENSO variance different 2,000 years ago compared to today? Because, yeah, I think that would bias my, given the data assimilation, for example, would just tend toward climatology. It would bias my result in that respect. So, yeah, I'm staying away from questions like that.
I am presenting the work of the Antarctica 2K group. The Antarctica 2K group was led by Barbara Stenian and Mark Curran. That took care of the data collection. Nearly Abram, Raphael, Neukom, and I did all the processing. And then Sancia, Gourceau, and Valérie Masson-Delmotte did the proxy calibration, and a lot of people contributed data and thinking and solved problems. Why are we interested in Antarctica? Nobody lives in Antarctica, but Antarctica is funny because it's not behaving. It's not warming. And so that's this picture you saw it Monday morning, nearly Abram showed it, and she showed that the onset of recent warming is around 1850 for most of the northern hemisphere, but the southern hemisphere seems to have delayed warming, and Antarctica seems to have no warming. And so that was for the graph on the left. And on the right, you can see models. The blue bars are models, and they tell you the onset of warming for models. And it tells you that models expect warming to start around 1850 everywhere on Earth. And so they match data nicely in the northern hemisphere, but in the southern hemisphere, they don't. And the question now we ask is did we do it wrong? Do we have, or is this signal real in Antarctica? What was published in 2013, that's in that paper, was based on 7 long ice cores. And we found a long-term cooling trend over Antarctica that didn't stop, basically. This time, we had 112 records. We call them high resolution, but they're not necessarily annually resolved because otherwise you don't have anything in the Antarctic plateau. And they are all already published, and the publisher decided that the proxy that we use is exclusively water isotope, so either delta OT or delta D was a proxy for temperature. Giving an example, Saipol Dome is not in this because on the paper that published Saipol Dome, they said there's a glaciological influence, this is not just temperature, so we didn't take it. And then they're cover 50 years and they're synchronized by volcanic tie points. Then we divided them into 7 regions because we wanted our stack to be meaningful. And we know that the climate in West Antarctica is nothing like the climate in East Antarctica. So we have a beautiful 7 regions. And this is here the correlation between the mean of each region and each and the grid of the temperature around Antarctica. And you can see that the Weddell Sea is in the Weddell Sea, and that the Antarctic Peninsula is highly correlated with the Antarctic Peninsula, so we think our regions make sense. And then we have water isotopes. We think they're a proxy for temperature. For those who don't know, I figure I should just say quickly why it's a proxy for temperature. It's a proxy for temperature because when you evaporate or you change phases, then there's a fractionation of isotopes. The heavy isotopes stay in the condensed phase, and this fractionation is sensitive to temperature. That's the first reason. So when I evaporate water out of the ocean, I have light isotope in the atmosphere, and then as I rain out the water vapor, I will get lighter and lighter in the atmosphere. And this whole process is temperature sensitive, and we call it Rayleigh distillation. At the very end, the last little snowflake that falls, this fractionation will also depend on temperature. And so water isotopes are a good proxy for temperature as long as the whole process is linearly correlated with temperature. And then we try stacking our data. So the first thing we did was to clean and to bin it. We binned it in 5-year averages, and that's important to us because there is a lot of deposition noise on the ice cores, and binning it by 5 years allows us to not have to have replicate cores. Then we made a stack, and we had 3 approaches. We don't have 7 or 8 like you guys, but first we just averaged the data in a region. The problem with that is that sometimes we have a part of the region that is better sampled, and that creates some bias. So then we did CPS, composite plus scaling, and that's a great method, except that in Antarctica, we often don't have a reference period. The observational period is really short, very little before 1980, and a lot of ice cores don't have the top of the ice core in ice, and so we don't have a reference period, and so we need to eject a lot of important records like Dome Fuji, so we don't like that. So instead, our third method was to use least squares, where we correlate the temperature at our site in the model with the regional temperature in the model, so that's purely model. We can keep all the data this way, and we pray that the model has the right correlation. And that also implicitly assumes that iScore is a good temperature proxy. The good thing is, all methods give us basically the same answer almost everywhere. So here you have the simple average is the color, and then the lines, the gray and more gray lines show you the difference. And there's one region where it's not the same, and this is West Antarctica. Here you have a big difference. And why is it? Because in West Antarctica, we have two records that have opposite trends, and that is not allowed. And these two records are waste divide, which shows a cooling trend over the continent, and waste divide is here in the middle, and it's well correlated with all of Antarctica. And the other is Roosevelt Island, which is an island in the Ross Sea. And when we did the weighing methods, either CPS or least squares, it basically didn't give a lot of weight to Roosevelt Island because it has a sensitivity to local climate, to sea ice that is not regional temperature. And therefore, we preserve the trend when we expel Roosevelt Island or give it a low weight, which we don't if we do a simple average. So when you do a simple average, you have almost no trend. And when you use the weights, then you get the trend back. But for all other places, then we have really something robust with our stacking. And what do we find? First thing we find is significant cooling trend over all regions. So I just plotted in the map the trend 0 to 1900. So it's in degrees per thousands of years. And you can see the trend is the largest in West Antarctica. And it's something like a degree and half a degree in the rest of the continent. And then over the last 100 years, we have warming in West Antarctica, in the peninsula, a little bit on the coast, but not in the continent. So to answer the first slide I will show from Neukom, we do have a warming trend, but only in certain regions of Antarctica. That's why we separated the climate in different regions this time. And why do we have warming? We know some things about why we have this warming trend. In the peninsula, a good part of it is linked to the southern annular mode. When the SAM is in its positive phase, the westerlies are more shrunk into Antarctica. So then the peninsula, which has the tip, becomes on the warm side of the front and can get a large warming. We know that the SAM has been increasing over recent years. That is partly due to the ozone hole. So part of that trend is due to that. And part of it started earlier and maybe not. But that's a mechanism for explaining why the peninsula should warm. And for West Antarctica, it is linked to what we call the Amundsen Sea Law. This is the second mode of variability of climate in Antarctica. It is linked to tropical teleconnections. Here you have, so that's the second UF. Here you have the ENSO onto the surface atmospheric pressure, so it's very similar. And there's been some really interesting studies showing that when you have convection in the central tropical Pacific, you have a Rossby wave train that basically locks in the position of the Amundsen Sea Law. And what happens is that where it is situated has a profound effect on temperature in West Antarctica. If the low pressure is over the Ross Sea, where is this thing? Yeah. Here, if it's over the Ross Sea, then warm, moist air will blast West Antarctica and you'll have a warm anomaly. And if it's over the Bellingshausen Sea over there, then the air masses go around and you have cool and dry climate. That's illustrated here. When the low pressure is over the Ross Sea, you have lots of precip and you have warming. When it's over the Bellingshausen Sea, drier and colder. And so we know that the warming in West Antarctica over the last 50 years can be attributed to changes in the central tropical Pacific. And another way to say this is it's possibly natural climate variability, not global warming. And we can see whether these warming trends are unprecedented by looking at these histograms, which show in color the 100-year trend of all 100 years in period in the last 2,000 years. And then the black line with its uncertainty bar is the last 100-year trend. And you can see for the peninsula, clearly the recent warming is outside of range of what we've seen for the past 2,000 years. but for West Antarctica, it isn't. So finally, my conclusions is that we have a significant cooling trend over the past 100 years for all regions that is strongest in West Antarctica, and that the recent 100-year warming trend is significant in the peninsula. It is linked with the SAM. Significant in West Antarctica. It's linked to the Amundsen sea low, which is not unusual in terms of natural climate variability and started after 1950. We don't see continental warming trends started in 1850 as the model see, and I can ask you why. That's the future work. You can read all of it in a soon to come out Climate of the Past. Thank you.
I would like to turn your last question back on you. Why do you think that you don't see a warming trend in the Antarctic sector? Could it be related to Southern Ocean, the door to the deep ocean being propped open, as others have suggested?
So I think there are hypotheses. One of them is that there are changes in the interhemispheric temperature exchange, so that there's more export of heat out of Antarctica that offsets the warming. Another would be that climate models are way too sensitive to CO2, and that maybe here we see more natural climate, and that's another suggested hypothesis. Yeah, I don't really know. I can say, though, that we saw these maps of the previous talk that were showing the maps of the warming, and they were having West Antarctica not cooling over the past 2,000 years when they were showing that, and so that's probably not okay either, yeah.
When you move from the previous reconstruction to the new one, the number of records has increased by a factor of 10. And so what was the main outcome due to this large increase of data according to your analysis? So does it change a lot, or finally the conclusions are more or less similar?
So I think it allowed us to precise the reconstructions per regions. So, and that's important because the dynamics of why climate should change in the peninsula is not the same as what it should change in the East Antarctic Plateau, and we're able to make this difference. But as far as the long records, we still don't have that many. So although we say we have 100 some, or a lot of them are 50 or 100 years old, and then the long records are still a handful. So that's not making a big difference. But I think the results from Waste Divide have come out very recently. Roosevelt Island is also the newest record, and they were not in the previous one, and that questions also, like there's a lot of uncertainty now with Roosevelt Island about how West Antarctica has been changing actually, because the trends are opposite.
So anyway, this was the second part of the Antarctica 2K community. So the first looking at the isotope records, and then I was tasked with coordinating the snow accumulation records. So I'm presenting this on behalf of a huge range of collaborators. Listed up here are the main writing team, but also it was the wider ice core community who actually provided the data. Let's try that. So why are we interested in snow accumulation? Well, the Antarctic ice sheet, obviously, is the largest reservoir of fresh water on Earth. Even very small changes in its volume will actually have big changes to not just global sea level, but actually the whole hydrological system. Changes to atmospheric circulation, sea surface temperatures, salinity, and thermohaline circulation. So it's hugely important. And recent studies based mainly on remote sensing and modeling, and the combination of the two has led to an understanding that actually there's been a mass loss in Antarctica in recent decades. However, it's worth noting that the uncertainties in some of these remote sensing techniques is actually really very large. And also, they're very much restricted to the satellite era, so pretty much from 1980s onwards. So if we want to actually have an understanding of, put these recent changes in context, we really need to introduce some longer records. So we can do this, and the best way of doing this is using the ice core records. Now, I've put up here, so when we talk about Antarctic mass balance, that's the combination of mass gains, so mainly through snow accumulation, obviously, but also mass losses. And then, so the main one being the snow accumulation. And this is what we can measure from the ice core. And we do this by using known dating horizons, and then obviously the gap in between those. So such as the seasonal deposition of chemical species, we can date the records annually. And so the main driver of snow accumulation is obviously going to be precipitation, but we also need to take into account some of the other processes that are involved, such as sublimation and melt. For most of Antarctica, this is actually fairly minor, but for some regions, particularly the coastal zones, this can actually be important. Obviously, with the records, they need to be corrected for density, and then the influence of thinning with depth. So the first thing to do was to set up the Antarctica 2K database, and we made the decision early on that we were going to only use records that were peer-reviewed, so published records. What we needed was that the records were annual resolution, and for us we decided they needed to cover the period, a reference period from 1960 to 1990. All of the records were corrected for thinning in various ways. We discussed this in the paper that's out at the moment. And based on all the records that are available, 144 of these snow accumulation records for Antarctica were submitted, but of these only 80 were actually eligible, which meant they actually met the criteria we wanted. Again, I mean, the map looks just the same as you saw for the previous talk, but essentially we wanted to divide up the snow accumulation and look at regional changes. So we again chose 7 regions, the exact same as the isotope study, but actually you'll see that some of our boundaries are slightly different. But essentially what we're really interested in doing is ensuring that we separate out the low accumulation high plateau sites, or East Antarctic Plateau, from the the higher accumulation, more maritime close to climate of the coastal zones. So despite our best efforts, what you can pretty much see from the map is that the spatial coverage is pretty poor. And it's also worth noting that the number of records we have is considerably less than the isotope records. And this is because although people have the isotope records and they have their snow accumulation data available, actually people aren't publishing it, so it wasn't available for this study. So particularly there's vast areas of the East Antarctic Plateau which we have very little data from. And this is because the snow accumulation at some of these sites is absolutely tiny. So it's very hard to be able to get an annually resolved snow accumulation record. Also, there's some regions around the coast which are undersampled. One of the things that we wanted to do, so I'm not going to go into too much detail about how we did the records, but essentially we standardized everything relative to this reference period, which we chose as 1960 to 1990. And then average them out by region. But what we wanted to avoid is any bias introduced by the sort of density hotspots. So if you see at the top of the map there, up in Johnny Maudland, we've got this, cluster of records, whereas we've got vast areas with none. So we chose just a grid point so that data within the same grid point was averaged together first to try and overcome this bias. What you can also see here from the figure at the bottom is that, we've got pretty poor spatial coverage, and actually temporally as well. Most of the records cover the top 200-year period, so 41 out of the total of 80 cover the period from 1800 onwards. But actually only 4 records go back 1,000 year, and of those only 3 extend for the full 2,000-year period. Okay, so once we've got all of our records, we've averaged them all together, this does help reduce the signal to noise that you get from an individual ice core. But what we want to make sure is that we still do have a meaningful record of snow accumulation and a regional signal. So one of the things that we did was to evaluate the records against precipitation fields, and you can do this from the Reanalysis data sets. The one that we chose for this study was the ECMWF, Era Interim data set, because this has been shown to reliably reproduce climate and particularly precipitation variability in the high southern latitudes. But as I said, snow accumulation isn't a direct proxy for precipitation. It takes into account some of the other potential losses. So we also used modeled surface mass balance, which takes into account some of the other processes involved. So we used the surface mass balance from the Regional Atmospheric Climate Model, RACMO, version 2.4. And what you can see here on the figure, these are the correlations for each region with this model output. So what we can see, I'm just focusing on the middle two here. We've got the Antarctic Peninsula and West Antarctica. And you can see that the red regions on the map are really good correlations. That if you can see the dotted lines, those are greater than 95% significance. So particularly for these regions, the regional composites that we've produced are representative of regional snow accumulation. However, it's not quite the case for all of the sites. So if we look at the collection of ice cores that we have from the East Antarctic Plateau, we seem to do a pretty poor job of reconstructing snow accumulation there. And the same is also true for the Weddell Sea region. Now, in the case of the Weddell Sea, that's because in that particular region we only have one ice core. So maybe it's just an artifact of the fact that we haven't overcome that large signal to noise that you have using just one record. And for East Antarctica, you could argue that potentially the models aren't able to capture the small-scale changes in precipitation occurring there. However, actually, there's not very much consistency between the ice core records themselves, so it could just be that in these very low accumulation, windy regions of the East Antarctic Plateau, that we're just not really getting a very good record of past snow accumulation at a regional scale anyway. Okay, so I said we were focusing on regional, and I think I'll explain a little bit later why this is so important, but I just wanted to jump back to continental scale, because this is what's been done previously. All the records have been, in earlier studies, all the records have been clumped in together to produce a continental scale record of what's been happening in Antarctica. So we did this same thing again. We separated into East and West Antarctica and also Antarctica as a whole. But what you can kind of see from the plots here, again, this is correlating with the RACMO data, is that actually in doing that, you just bias towards either the region where you've got the most data, or in the case of for the West Antarctic one, you're biased towards the very high accumulation Antarctic Peninsula that's dominating the signal. And the effect that you have by combining everything into one continental reconstruction is that you just lose your significance for any region. So, because we had such good agreement with between the composite records and the surface mass balance from the RACMO model, we then converted our records into surface mass balance to give us some really meaningful numbers back through time. And these are the records for each of the regions, plotted back just to 1800. And what you can see clearly, quite a lot of decadal variability. But all the regions, with the exception of the Wilkesland region, show an increase in trend in surface mass balance since 1800. So in some regions, this is quite small, but in particular for the Antarctic Peninsula, this is an increase of 1.8 millimeters per decade of increase in surface mass balance. But there is a difference between the two decades. So particularly for West Antarctica, Johnny Maudland, and also Victoria Land. So there's increasing trends overall since 1800, but actually during the 20th century, we see a decreasing trend. And for some of the changes, particularly if we look in at West Antarctica into the most recent period, there is actually some very big jumps to high accumulation changes. But the trouble we have is that we've still got relatively few data points, so it's hard to kind of assess some significance onto those ones. And it does appear that potentially some of these changes, well, they look fairly natural. But one thing that does look unusual is the Antarctic Peninsula, and certainly over the 200-year period, the changes that we see here in the most recent decades, certainly towards the end of the 20th century, you know, as we've seen from previous studies, is actually looking outside of what we would expect. Now, obviously, what we really wanted to do from this, and what we were kind of asked to do from this, was to extend the records further back in time. But it actually becomes quite hard because we're very limited with the number of records we have. So we've included all the records here back to over the full 1,000-year period, and you can see that we pretty much lose the Antarctic Peninsula quite early on, the same with Johnny Maudland. And then the records that do go back, you can see this very large jump to increased variability, and this is just an artifact of the fact that we're going from multiple records down to single records. But some of the things that we did try and look at here was that going back 1,000 years, you actually have very little consistency between the regions, not very much that you could kind of draw from it. So to kind of sum up then, what we had was we combined all of our regions together, we area weighted them, And then we can actually come up with some real numbers to say what the changes were. And so we can say that actually for the last 200 years, there's been an increase in surface mass balance of Antarctica of 44 gigatons. And the largest contribution from this has actually come from the Antarctic Peninsula. And this is really important because previous studies have drawn conclusions that there's actually been no change in Antarctic surface mass balance over the last 50 years. And actually, they've extended that back to over the last 800 years. But what we found from our study is by including a lot more records, producing this database, is that actually that simply isn't true. So I'm focusing on here on the changes just in the last 50 years, and you can see that the Antarctic Peninsula really jumps out at you. So this 72% contribution of increased mass in the Antarctic Peninsula, it can't be counterbalanced, if you like, by some of the decreases that we see elsewhere. So it's really important that we do, in doing these studies, is that we look at things regionally. We ensure that we've got enough data coverage so that we don't miss out places like the Antarctic Peninsula, which are making such a large contribution. And I'll just put up my summary there. So essentially, we did a review of all the records and reconstructed this, tried to extend it back to 1,000 years. But the kind of take-home message is there has been a big increase for Antarctica as a whole of 44 gigatons. The majority of this is from the Antarctic Peninsula, a region that's been missed in previous studies. So, and I think I'm getting rushed off. So, thank you.
You mentioned on the east that, I think it was the east, that you didn't have very many records, or they were lower resolution. What would happen if you relaxed your annual resolution criteria? How would the picture change? Would it change?
We still don't have that. It's not that we have a whole load of low-resolution records that we kicked out. They actually just don't really exist. So most of the records of snow accumulation from the central Antarctica, sort of around the Vostok station, are done from state measurements. So it's actually quite hard. I mean, this goes to how do you bring in something of very low resolution in the order of several decades to compare with changes at an annual scale. So I think for this study, it was just beyond what we could do. But for the community, it's something that we need to think about how we can utilize some of these much lower resolution records.
Okay, so after the continent and the ice core, so we're going to switch to the marine environment and to speak about sea ice dynamics and the potential forcing mechanisms. So this over the last 2,000 years. Antarctic sea ice, the seasonal cycle of Antarctic sea ice has a very profound impact on the southern hemisphere climate through the energy balance, the atmospheric circulation, the oceanic circulation, and the CO2 through the pumping of the by the biological pump. Over the last decades, Antarctic sea ice has increased, as you all know, but this... Okay, sorry, didn't know. So I'm a movie star, so Ellen was a singer of the movie star, okay. Sorry, I don't like to stand up like this. So the global increase hides some spatial heterogeneity with a strong increase in the Weddell Sea here, and a decrease in the Amundsen Sea and Bellingshausen sectors. And although we don't really know about the spatial heterogeneity and about the trends over the instrumental data, because they're not so long, they're not long enough, we think that large-scale atmospheric patterns, like the input of warm air to the Antarctic Peninsula, or the flow of cool air from the Ross Sea, will increase here the sea ice and will decrease sea ice over there. A second process is maybe also the structure of the vertical structure of the water column that may decrease also the heat content towards the atmosphere. And this is maybe because these processes are not well represented in climate models, that these ones cannot reproduce the evolution of sea ice over the instrumental data, and this casts doubt on the future projection for the 20th century. So this is why it's important to turn off to the recent past, to try to document first sea ice evolution and to try to understand the forcing mechanisms behind this evolution. So this is what we did. The IOD program retrieved a 180 meters long core, drill core, in 2010 of the Adelie Land in East Antarctica. And based on 80-something C14 dates, this core covered the last 11,000 years with a mean sedimentation rate of 2 centimeters per year. So many proxies have been applied to this core, but our group, we worked on diatoms and diatom biomarkers that were performed every 5 to 10 centimeters, giving a decadal resolution to the records. And we're going to focus today only on the last 2,000 years, it means the last 40, the upper 40 meters of the core. A brief word on the proxy. So the diatoms, the algae living in surface water, and some of them are living in very, very cold water with very, very sea ice cover, and so they are sea ice proxy. Some other ones are living in warmer waters where sea ice is not present, and they are called also open ocean proxies. About the biomarkers that are synthesized by the diatoms, we are speaking here about lipids. Some with double bonds are synthesized only by sea ice dwelling diatoms. Some others are synthesized by diatoms living at the sea ice edge, and the ratio of the two, so the double bond to the triple bond, are decreasing from the coast to the open ocean, and we think these represent a sea ice proxy, so extended sea ice proxy into the summer. So these are the results we obtained over the last 2,000 years with the recent on the right of the graph. So here you've got the sea ice diatom proxy. Here you've got the biomarkers I was talking about. These Caterus resting spores are the diatoms that are representative of open water conditions, along with this one here. And the 30 Antarctica are representative of autumn sea ice. So I'm not going to go into details with these, just by blocks. So the first period here, from 0 to, let's say, 500 years CE, we can, all the proxies argue for a late sea ice retreat, a very short rain season, and a weak polynya activity of Adelie Land. The second period, between, let's say, 500 and 800 CE, you've got an early sea ice retreat, late sea ice freezing in autumn, a very long rain season, and a strong polynya activity. The third period, here, during the 800 to, let's say, 1500, something like this. So the proxies are used for a late sea ice retreat, a short growing season, and again, weak polynya activity. And finally, the last period here, between 1500 and 1800 CE. Again, the proxies says that there was an early sea ice retreat, early sea ice freezing in autumn, a short rain season, and a strong polynya activity. So when you have these environmental conditions, we start to try to see whether this was a very local signal or a regional signal. So we compare here the sea ice proxy reversed on the y-axis to oxygen isotopes in tall ice and Lodom. And, well, there is let's say, quite a good agreement between the records where you've got here less sea ice of Adelie Land here, and warmer temperatures in tall ice and Lodom, and again go back in time. So we think that there is kind of that our records represents a regional signal over the Indian sector of East Antarctica. And then we look for the potential forcing behind this evolution. And we compare first our record here, so the Fragileiopsis curta group, so the sea ice proxy, with external forcing, so the volcanic events, and the solar irradiance here. And in fact, we found no real agreement, no synchronism at decadal to centennial time scale between the external forcings and the sea ice response. Although this is worth noting that the volcanism episodes here, they are congruent to the SAM+ phases, which support the studies by Magro in 2016. So then we compare our records to internal variability. So here the spring sea ice with the SOI, so the Southern Oscillation Index, and there is a fairly good agreement between the two records here, which is congruent, which is in agreement also with the modern climatology of Antarctica, where there is a positive correlation between the SOI and the temperatures in the southern hemisphere, and especially that La Nina here induces a warming over in East Antarctica. And also in the studies, it's noted that the ENSO is much better expressed in spring, and this is exactly what we have here with La Nina-like episodes in phase with less sea ice, so warming in our region. Then we compare also the autumn sea ice proxy diatom-based with the SAM index that Neroli published a couple of years ago. And again, there is a very good agreement between the SAM index and the terrestrial Antarctica of the last 1,000 years. And this is also an agreement with the modern climatology of Antarctica, whereby a negative correlation between the SAM and the temperatures have been inferred for the last decades, where SAM plus phases induces a cooling over East Antarctica in our region, and that the SAM is much better expressed in autumn. So when we have potential forcings, after that we looked for the mechanisms behind this. And we thought that this is a couple action of atmospheric and oceanic circulations, where the phases for when we've got a lot of sea ice close to the continent here in the IODP core, so phases 1 and 3, the environmental studies from the southern hemisphere argue for a polar position of the westerlies. And in Delworth in 2008, this ocean atmosphere climate model, they showed that in this situation, there is a cooling of the surface water close to the coast, the Antarctic coast, due to the outpouring of very cold water. So supporting more sea ice during these periods. And conversely, during the periods 2 and 4, when we've got less sea ice in the off-Adélie lands, the environmental studies indicate an equatorward position of the westerlies and inducing a warming around the coast of Antarctica, so in phase with our reconstruction. The corollary of this is that there is an antiphase, an opposition of phase between the coastal area of Antarctica and the conditions, the climate conditions in the polar front zone. And this is exactly what we obtained in this core here, that we produced temperature. I mean, we obtained the results like a couple of weeks ago, so this is brand new. So I plotted here in black the summer temperatures produced at this core around the polar front zone in the southwestern Indian of the Southern Ocean. And you see that when we've got, for example, in phase 2, less sea ice here close to the coast, we've got also very cool waters here towards the polar front zone. So in phase here with the model by Delworth in 2008. So as a conclusion and opening to this, the main conditions during phase 1 and 3 are non-correlation in the sea ice system between the coast and the open ocean, where you've got compacted sea ice, but the sea ice by itself is less extended to the north, and this is due probably to the coupled action of polar winds, position of the westerlies, that upwell more cold water to the south, but in the same time there is also a polar penetration of subtropical waters to the north that reduce the extent of the sea ice. This will induce less Antarctic bottom water formation to the south, but also a stronger northward flow of Antarctic intermediate waters in the subsurface layers. And these two processes will probably enhance the AMOC, and this should warm the North Atlantic. And obviously, for the other periods when you've got the opposite phase with a loose sea ice to the coast, but the ice will be more extended because of more katabatic winds. And this is due to equatorward position of the southern westerlies and less penetration of subtropical waters. This will produce more Antarctic bottom water and a reduced flow in the subsurface layers that will reduce the amok, and this should cool the North Atlantic. Thanks a lot.
Am I right if I say that we have seen quite a few reconstructions today for one particular season, but what you explained from your record is that the different seasons behave quite differently, and that's an additional complexity for the system?
Yeah, if you believe the proxies that we have, that we constrain with modern periods, looking at the distribution of the diatoms in the Southern Ocean, and also the piling up, the seasonally piling up of these diatoms. Yes, exactly. There is a different seasonality in the CI system close to the coast, and the forcing is probably different. I mean, different kind of modes express themselves during spring, another during autumn, and force the sea ice at the time scale.
Okay, so even though you saw in the last presentations that statistical reconstructions can be are usually quite good, they can have some issues. For example, in this case here on the upper right, where we see a change from basically historical documents to instrumental data. This shift might be in homogeneity in the data, or also spatial patterns and spatial reconstructions, if they're made statistically, can have inconsistencies, having very warm grid cells right next to very cold grid cells, which is probably not physical. And they are usually just having one variable at a time. So on the other hand, we have climate models. They are multivariate, they are spatially, temporally complete, they are physically consistent, and they follow forcings, but they don't follow the true evolution of the weather because they have internal variability. So our question is how to combine the best of the two. And the way that is done very successful in weather prediction and also in reanalysis is that you do data assimilation. And that is usually done, as it was pointed out just before, that you first start with an initial guess, then you run your model for maybe 6 hours, and then you have some ensemble spread, and then you have some new observations that you can assimilate, and then you have a new best guess, and then you continue with your next forecast forward in time. And now the question is, can we do something similar, or how can we do that in the paleoclimate context? If we have our really indirect, noisy, spatially sparse, and even temporally aggregated data. And the way we are doing it is by a method that we call ensemble Kalman fitting instead of filtering, to make the meteorologists a little bit less mad at us. And what we are doing is that we run an atmospheric model, Echam 5.4 in our case, and we ran it for the last 400 years, and we ran 30 ensemble members with all forcings. And we run that whole simulation in advance, so we do also an offline assimilation. We don't stop the model run and start it again after assimilating. We just run it completely first, and then we assume that this ensemble spread of the 30 members covers the whole range of possible climate or atmospheric states, and that is just constrained by all the forcings. And on the other hand, we have our observations, and in our case, that were early instrumental measurements of both temperature and sea level pressure. Then we also used monthly indices from historical documents, and we used tree ring information, tree ring width, and tree ring density. And as we also heard before, to use these tree ring information, we need forward models or proxy system models that translate then the model units of temperature and precipitation into the proxy units like tree ring width. And in our case, we are using a multiple regression model, so we take into account that tree rings at some locations just respond to August temperature, while in other locations they respond to May to September temperatures, or even precipitation as well. And in the future, we will even plan to advance it more and use really more sophisticated tree ring models like Xavier slide. But at the moment, it's multiple regression. And then we need some covariance matrices that we can calculate from our model ensemble to spread this information in space. And for the observations, we also need some error estimates to know how much we can trust our observations. We also calculate a covariance matrix of the observations, and then we can integrate that all in this Kalman filter-like approach and calculate our analysis. And the great thing in having this offline assimilation is that we can repeat it very efficiently also with if new data sets become available. So that's the network of data that we used. Of course, that is changing over time. And you see in the beginning, at 1600, it's much more proxy information, and that is then declining over time, because as soon as we have instrumental information available at the same grid box, we don't assimilate the proxy data anymore, because we assume that the instrumental observations are a little bit more trustworthy. Yeah, so and one last thing maybe to the method is that because of this assimilation of the tree rings, which are a growing season, half-year signal, our assimilation time step is half-yearly. So I assimilate data every half year, but in the state vector of the atmosphere, there's monthly information for the last 6 months. So our final product is monthly. We update our data on a monthly basis, but we also integrate in there the seasonal information. And what is also important for the tree ring proxies, as it was noted by one comment before, they might be statistically very differently treated and have different low frequency variability. And because we have a hard time judging what is the right one, or we cannot manage to process all records again, we build averages or anomalies around a 70-year running mean. So that means that the centennial variability in our reconstruction or our Reanalysis stems from the model simulations, and we only get the annual to multi-decadal variability in there from the proxies that we assimilate. So let me show you now how the results look. If we zoom in just onto a few years here, 1915 or 1953, for one grid box in Norway, you see the original ensemble spread is this gray band here for temperature at the top. And after our assimilation, we come up, the spread gets reduced to the red band that you see here. There's still some uncertainty in our ensemble, but it could be much reduced due to the assimilation of the data. And as you see, we are very often close to the blue line, which is the observations at that place. You also see that, of course, then this reduction in ensemble spread is not the same in space. We can mostly reduce the spread where there is a lot of spread, which is in northern hemisphere continental land regions, in continental land regions, basically. And also where we have data that we can assimilate, and that is mainly in the northern hemisphere. And in the tropics, where we already have little spread in between the ensembles and few proxies to assimilate, we cannot reduce it much more. And what you see also that we reduce then, due to the covariance structure, we not only update the temperature information, we also change our precipitation information and all other variables that are in the climate model. But you see here, precipitation is a very local and difficult signal, so we can shrink our spread from the original model ensemble a bit, but we cannot do it as good as for temperature, and also the match between observations and reanalysis is by far not as good as for temperature in case of precipitation. Still, if we look at correlations, and this is just the increase in correlation between our between the original model simulations before the analysis, the assimilation, and CRUTS, and then so the increase that the assimilation brought to it. The original model simulations already correlate with instrumental measurements because they have the forcings included. So this is just what was gained by the assimilation here. And you see that in the northern hemisphere, we can gain up to, 0.7 in terms of correlation coefficients for temperature. Clearly less for precipitation, but we can also, in nearly all locations, we can increase at least the correlation between the precipitation of the original simulations and then our reanalysis product. So this is just the same for the RE statistics. Looks quite the same, not as good for precipitation. There you see we in absolute values, we are a bit further away. Of course, we can also average our spatial fields into global means or northern hemisphere land means here, and we are quite close to previous reconstructions and also to instrumental data. But what is probably much more interesting is now to look really at the different variables and to the dynamics. This is an example of the summer 1816 after the big volcanic eruption of the Tambora, where we had a very cold and wet summer in Central Europe. And you see here a little bit was already in the model due to the aerosol forcing and the reduced solar input. But after the assimilation, we get much more of this cooling here in Central Europe, and we also see a low pressure anomaly. And if we now look into precipitation, we see that the original simulations hardly had any of these wet anomaly here, while our assimilation then really picks up this strong wet anomaly in Central Europe. And we can now go into the dynamics and also see that this was caused by enhanced westerlies that brought moist air from the Atlantic. So to sum up, I hope I could convince you that this, in brackets, data assimilation in the paleoclimate sense is still a useful approach to combine models and paleo data with all their related uncertainties to calculate the most likely state of the atmosphere, not just for one single variable, that it overcomes quite a few assumptions that statistical reconstruction had, that it works also well with spatially and temporally limited input data, and I find it quite useful to see that also this reduction of ensemble spread, which is different in space and time, can give us some information about how much we can trust our analysis product. So if you want to read more about it, it was just accepted in Nature Scientific Data and should be published there in the next couple of weeks. The data will all be online freely available, so you can all use it and analyze it if you like. And just a last thing to mention is we have also a poster. Veronica Waller used the same method with the new Pages 2K data set, so just assimilating proxy data of tree rings, corals, and ice cores. And if you want to read or learn more about it, come to poster number 19 outside. Thank you.
I'm curious about your monthly reconstructions. Do you have any sense for how well a monthly reconstruction does globally when you only have tree rings? Like it seems to make a lot of sense to me when you have pressure observations, say during the modern era. Where it doesn't seem to make sense to me is when you just have tree ring data.
Yeah, obviously then we see that we have the skill only in the summer months. So we won't, in the winter, we probably, if we only assimilate tree ring data, we purely have just the model in the winter season. If we don't have any, then that's why we also used indices from historical documents, because they give us then some information about the winter. And if we just use tree rings, at least we can then say the tree ring at that specific site is only giving us information about August temperatures and not about the whole year. And yeah, but in the other case, we will just see that we have still a large range of possible atmospheric states, and we didn't reduce the spread of the ensemble at all in winter. So in this case, I think it's a bit more honest using the proxies for just what they are, but yeah, for winter, then we don't have any improvement over just the pure model simulation if we don't have any other information that includes winter information.
I couldn't remember the map at the beginning of the proxies, but it was surprising that you didn't get better estimates of precipitation in, say, the American Southwest. It seemed to be just as poor there. So I can understand the high latitudes, we do well for temperature in the summer. But in the American Southwest precip, why was that poorly constrained?
Yeah, we have really a limited data set of tree ring proxies at the moment in this product. So that is basically just the whole MXD network plus a few selected tree ring width records that are good temperature recorders. So that's why we now changed also to using the whole pages data set, and we will probably change to more using something like Nathan and colleagues are using in their LMR project, where we use also Petra Breitenmoser's whole collection. And yeah, we have to enhance our network to become better, especially going further back in the past.
Could you clarify which SST you used for your model simulation?
Okay, yeah, we are using the Reconstructions by Michael Mann, obviously because there was nothing else to use back to 1600, but then we superimpose some El Nino signal. So we take El Nino from model simulations and then use El Nino reconstruction, I think by Ed Cook, to superimpose that signal onto the SSTs. So it's basically the Mann reconstruction plus an El Nino signal.
We know that ensemble Kalman filter assumes that everything, I'm here.
That doesn't help.
That everything is Gaussian, but in reality, we know that the positive quantities are not Gaussian. Do you have any plan to to deal with this problem of the ensemble Kalman filter in future?
Yes, so quickly, yeah, we have to assume that it's Gaussian.